I welcome you again for this NPTEL online course on earthquake geotechnical engineering, and we are at lecture number 37, which is for liquefaction of soils. And what we are going to discuss in this module 4th, we already covered introduction, liquefaction susceptibility, we already partly covered initiation of liquefaction. So, in this initiation of liquefaction, what the topics flow liquefaction surface as well as influence of excess pore pressure EPP has been covered. Evaluation of initiation of liquefaction using cyclic stress approach has been started, and we already covered characterization of earthquake loading based on simple methods and ground response analysis. So, the characterization of earthquake loading is over in the last lecture. Today in this lecture number 37, we are going to talk characterization of liquefaction resistance based on laboratory as well as institute test. In fact, laboratory based on the laboratory test have been already started in the last lecture, and in this lecture we are going to have continue with based on the laboratory test and based on the institute test. As for the institute test is concerned, we will be having characterization based on 3 types of institute test. One is standard penetration resistance, then cone penetration resistance and the shear velocity. So, in this lecture we will cover based on the SPT, and then the next lecture we will be covering based on the cone penetration and shear velocity. Coming to characterization which is based on the laboratory test, we continue, and if you recall that this curve which is called cyclic strength curves has been discussed just in the last lecture. So, I will not repeat because that is you can have the consult the last lecture for this one. Now, what we are going to discuss in this lecture, how to use these curves if these curves are generated from the laboratory data, and if suppose these curves are available to you, how to use this curve for like calculation in the field for the field. So, one of the example we are taking it here. What is in this example? A 2 meter thick layer of, and this is from California Sacramento River sand, and the properties of the layer E Young's that is void ratio is 0.87 and phi is 33, and these properties are for this layer, this second layer 2 meter thickness, and this 2 meter thick layer is overlain by 4 meter compacted fill, and the effective overburden pressure is 91.3 kilopascal, which is at the middle of the layer, which we will check and show it. The water table is at the bottom of the fill, which you can see here. Using the cyclic triaxial results, the question is the estimate the maximum cyclic shear stress which is required to initiate liquefaction in the sand in a magnitude 7.5 earthquake. So, this is the sand layer here, and it is compacted fill layer. On the top of this you have compacted fill layer. The top layer is consist of compacted fill, and so we need to find, because see water table is here. So, above water table because the soil will not be susceptible for liquefaction. So, we need to see the susceptibility of the sand layer for the liquefaction. For this what we do, we first of all find at the middle of the height of the layer effective overburden pressure, which will be 4 meter into 2.1 for the top layer plus 0.91, 1 meter is the thickness and 0.91 is the submerged unit weight, because it is saturated and you are calculating effective overburden pressure. So, as a result here we need to use the submerged unit weight, this submerged unit weight rather than total saturated. Then it is G. So, rho into G will be gamma 9.81. So, ultimately you get 91.3 kilopascal, and this 91.3 kilopascal is very near to the data which is available to you from the lab, which is the data available is done is at confining pressure, effective confining pressure 100 kPa. So, these curves are at effective confining pressure 100 kPa. So, because this is very close to what is we are getting at the middle layer, so as a result we can use these curves for our analysis. So, what is these curves? Cyclic stresses which is required to produce initial liquefaction and 20% axial strain in isotropically consolidated Sacramento River sand, a triaxial specimen, and which is after Seed and Lee of these curves are from the after Seed and Lee of 1965. So, this is like we already discussed that what is one y axis and x axis. So, what is done here? first of all we are talking about the sand layer. So, the sand layer E equal to 0.87 here, right. So, as a result we need to use a last curve which is for E equal to 0.87 from this, and in this last curve we need to first select the what is the amplitude of cyclic Davidic stress which is coming in. So, amplitude of cyclic Davidic stress can be calculated. First of all, a magnitude 7.5 earthquake is expected to produce about 14 uniform cycles. This we already discussed. If you recall, like number of like cycles, there was a curve and this kind of curve was there, a line, and this was going like this, and here you have number of cycles n, and here you have magnitude here, and here you have n. On x axis number of cycles was there. So, then you can read the number of cycles from this, and this number of cycles related to you get 10 for 7 magnitude earthquake. So, if this is for 7 and this is 10. So, the number of cycles was 10 for 7, but for 7.5 it was 14 uniform cycles, and for 14 uniform cycles we read the direct the Davidic stress from this curve. So, what I do, I need to use this one. So, this is 14 here somewhere, and you find out 40 will be here. So 14, because it is log scale, so 14 will be somewhere here. So, about you get, so what you get for 14 cycles, it get about 39 or so, 14 will be somewhere here. So, it comes about 39 kilopascal. So, for 14 cycles from using this chart and using the last curve, you read the value is 39 kilopascal. Now, for phi equal to 30 degree, which is given for this soil layer, K naught can be calculated as 1 minus sin phi 0.46. For this K naught we calculate what we call the CR, correction factor, which is 1 plus K naught divided by 2. So, you get 0.73. Now, CSR triaxial can be calculated sigma dc by 2 sigma 3c. So, 39 divided by 2 and sigma 3c is 100, so 0.195. CSR field will be 0.9 into CR into CSR triaxial. So, what we get in the field 0.9 multiplied by CR into this one. So, if I put the numbers, then I get 0.128, and for this CSR field toe cycles can be calculated simply CSR field multiplied by sigma V naught. Here you need to understand this is effective overburden pressure, it is not the total. So, this will be the CSR field multiplied by, because the CSR is calculated based on this the effective overburden pressure. So, you get 11.7 kilopascal. Once you get this is the average toe cycle. So, toe max will be if I divide this value by 0.65, then you get the maximum shear stress which is 18 kilopascal. So, this way a peak shear stress of 18 kilopascals would be required to initiate liquefaction in this layer of. So, the here in this layer, middle of this layer, the cyclic maximum shear stress toe max which is required for the liquefaction to occur will be 18 kilopascal. So, this much stress will be required. So, this is the final answer, that you require a stress of cyclic shear stress of 18 kilopascal to start the liquefaction, to initiate the liquefaction. Now, this was based on the laboratory test. Simply continue with the laboratory test, characterization based on the laboratory test. These tests can also reveal the manner in which the excess pore pressure is generated. For stress controlled cyclic test with uniform loading, Lee and Alibaisa in 1974 and D'Alba et al. In 1975 found that the pore pressure ratio Ru is related to the number of loading cycles by this relation, which is simple relation, half means 0.5 and here sine inverse. So, in this case in the bracketed quantity is just a ratio, you get n by nl and 2 multiplied by 1 by alpha. Suppose I get alpha equal to 1, then it will be simply n by nl minus 1. So, when if you put the value of, you check this relation, if I put in this relation n equal to, in this relation if n is put as equal to nl, then what will happen? Irrespective of any value alpha, the bracketed quantity will be 1 and sine inverse 1 will be pi by 2. If I get the sine inverse 1, then it will be pi by 2. So, then 1 by pi, so it will be half plus half. So, in that case when n equal to NL, the RU you obtained from this relation is 1. So, simply at n, when n equal to NL, your pore pressure ratio is 1 from this, and this is expected. So, using this equation, where what is in this equation NL, NL is the number of cycles which is required to produce initial liquefaction. Naturally, the value of n cannot be more than NL, maximum value of n is NL, and when n is equal to NL, then RU equal to 1, and alpha is a function of the soil properties and test conditions. For example, for alpha equal to 0.7, the chart is like this here, the dotted line, this dotted line is for this curve is for alpha equal to 0.7. Here in this case, when n or this ratio n equal to NL is equal to 1, then RU is 1, but when this n by or NL equal to 0, then RU will be 0, because n equal to 0 means there is no cycles, so in that case there is no chance of liquefaction, because there is no loading basically. So, here this is rate of pore pressure generation in cyclic simple shear test, and these curves are nothing but they can be generated using this equation which we have already discussed. So, this was characterization based on the laboratory test, and for this, for a number of years liquefaction resistance was commonly characterized by cyclic stresses determined from laboratory test. However, subsequent work showed that cyclic stress based measures of liquefaction resistance are influenced by factors other than the initial density and stress conditions. For example, liquefaction resistance is influenced by difference in the structure of the soil or soil fabric produced by different methods of specimen preparation. So, as a result, the history of prior seismic straining also influences liquefaction resistance. For example, liquefaction resistance of a specimen that has been subjected to prior seismic straining is greater than specimen which are not subjected. Also, this liquefaction resistance will increase with increasing over consolidation ratio and lateral earth pressure coefficients. So, that means the liquefaction resistance depends on many other factors which perhaps we are not accounting in the laboratory. For example, prior straining, because a sample in the field is subjected to the prior straining, or maybe over consolidation ratio is different, or lateral earth pressure coefficient. So, in that case, so many factors are there which you are not accounting in the laboratory when doing the cyclic triaxial test or simple shear test. As a result, many of these factors, which is for example soil fabric, the history of prior seismic straining, OCR, then you have K naught that is the coefficient of lateral pressure at rest, length and time under sustained pressure, influence liquefaction resistance, and difficulty in obtaining truly undisturbed samples, suggest that liquefaction resistance should be characterized as far as possible based on the in situ test. So, now we will switch over on the in situ test. We complete characterization of liquefaction resistance based on the laboratory test, and we are going to start characterization based on the in situ test. When we talk about in situ test, we already discussed that we are going to using 3 types of test. One is based on SPT data, standard penetration test data, then second one is based on the cone penetration test data, and third is based on the shear velocity data. So, coming to this one, characterization based on in situ test. So, previous case histories can be characterized by the combination of loading parameters, 2 parameters, one is loading parameter which is L, and another is liquefaction resistance parameter by R, which can be plotted with symbol that indicates whether liquefaction observed or not. A boundary can then be drawn between these 2 parameters that have and not produce liquefaction. For example, here is the case. Here on y axis you have the loading parameter, on x axis you have the resistance. So, naturally when the resistance is more than the loading parameter, then the liquefaction will not occur. So, if I go along this axis more, then no liquefaction will occur. If I go more on the y axis, then liquefaction will be observed. So, in this case the solid circles, black dots, they represent the positions where the liquefaction was observed, while the hollow circles are the case where the no liquefaction was observed. So, continue with based on the it is and this boundary is normally drawn conservatively. So, to be on the safer side, usually the cyclic resistance ratio, which is called CRR in the short, is used as the loading parameter, and the institute test parameter that reflect the density and pore pressure generation characteristics of the soil are used liquefaction resistance parameter. So, in fact, on the x axis liquefaction resistance parameter may be your standard penetration resistance, it could be cone resistance, or it could be a shear wave velocity. While on y axis in all the three cases we have one parameter which is called cyclic resistance ratio or CRR. So, now let us discuss based on the standard penetration. In fact, most of the studies which is based on the field test are used standard penetration test data. Why? Because standard penetration test data, SPT data, are widely available. These are the tests conducted, and they are not only popular in our country India, but they are worldwide very much popular including in Japan or USA. So, this because, and the simple reason being that standard penetration test, because you can get the sample also. So, they are, so in the standard penetration test has been widely used as the institute test characterization of liquefaction resistance. Factors that tend to increase liquefaction resistance, for example, density, prior seismic straining, over consolidation ratio, lateral earth pressure, and time under sustained pressure also tend to increase SPT resistance. So, this is very important, which goes in the favor of institute testing, that better we go for institute testing for liquefaction resistance rather than only simply laboratory testing, because some of the factors which influence the liquefaction resistance, for example, written here, density is there, prior straining, over consolidation, they will also increase the SPT resistance. So, as a result, SPT resistance is already, like suppose you have SPT data. So, n value will reflect having the effect of these factors which may not come in the laboratory data. So, the initial work was like by Seed et al. 1983, compared the corrected SPT resistance which is said in N160, there is a term N160, and cyclic resistance ratio CRR for clean sand and silty sand sites at which liquefaction was or was not observed in earthquake of magnitude 7.5 to determine the minimum CRR value at which liquefaction could be expected in a clean sand of a given SPT resistance. The following chart is prepared from these three data, that is Pan American data, that is all over the America, then Japanese and Chinese. So, this chart is there, and the data, different data are listed here, the different notations, that these are from US, these are from Japan or China. Now, what you have in this curve? You have three curves, and in these three curves the lowest one is for less, the percentage fine is less than 5%, 15%, 35%. And this SPT clean sand base curve is for magnitude 7.5 earthquake, and this is from a paper, research paper by Yao et al. In 2001. So, what is here? On x axis you have corrected blow count N160. What is N160? We are going to discuss in detail later. That is the corrected value of SPT resistance, that is the N value, where N is the number of blows in a SPT. So, you have number of blows, and this has been corrected for 60% hammer energy and at the 1 bar effective overburden pressure, which we will discuss. So, once N160 is there, so what we do from this chart, for given value of N160, for example 20, we pick up the value of cyclic resistance ratio. Here in this chart both are written cyclic stress ratio or cyclic resistance ratio, but we will stick with one of them, that is CRR only. So, we will, when we read this chart, we say that CRR is obtained from this chart, the value of CRR in the short cyclic resistance ratio. So, the liquefaction potential assessment procedures may be used with either standard penetration test blow count or cone penetration test. So, this is like what we are going, or maybe the shear velocity which is measured within the deposit, which is described as follows. And what we are going to discuss later, they are basically based on the code IS 1893 part 1 2016, and in this code there is an annexure F, and annexure F is nothing but it describes the simplified procedure for calculating the liquefaction potential. So, because this code Indian standard is easily available, so I will suggest that you go through that annexure F of the code. Now, evaluation of liquefaction potential as given in this code, what we are going to discuss is already given in the code. I am going to explain each and every step one by one. but the data which is shown here is coming from the IS code. So, in the step 1, the subsurface data which is used to access liquefaction susceptibility should include the location of the water table, number 1. Naturally, you should know where the water table is there, either SPT blow count N or cone tip resistance QC of a CPT cone or shear velocity Vs, 3 data. You require either N, QC or shear velocity. Then beside out of these 3, 1 data is required at least. Then you need unit weight of the soil and fine content of the soil. That is, what is fine content? Percentage by weight which passing through the IS standard sieve number 75 micron. So, which passes through the 75 micron sieve. 75 micron sieve can be said as a 0.0 75 mm. So, 0.075 millimeter sieve. So, these are the data required in step 1. Second step, evaluate total vertical overburden stress, that is sigma V0, and mind it here it says total, not effective, and the second effective vertical overburden pressure. So, both total is also required and effective is also required, and this need to be calculated different depths for all potentially liquefiable layers within the deposit. So, this need to be calculated for all the layers, and we will discuss one example on this, and then all the steps will be very clear. Then in step 3, what we need to find? We need to find the stress reduction factor RD, which can be found out using either of these 2 equations which we already discussed in the last lecture, depending on the depth Z, where Z is the depth in meter below ground surface. Once RD and the sigma V naught is noted, then you can calculate cyclic stress ratio, which is called in the short CSR, which is induced by earthquake loading, is given by this relation CSR equal to toe average, and this is toe average need to be divided by the effective overburden pressure. So, in this case on the right hand side you have everything dimensionless, 0.65 Amax by G, Amax by G will be dimensionless because Amax is represented in terms of G, and another ratio total overburden pressure divided by effective overburden pressure multiplied by RD. What is RD here? RD is reduction factor due to the depth. Amax is the peak. So, sigma V naught and sigma V naught, they will depends. Normally in this case this will be gamma into H Z with the depth, and this will be gamma effective. This will be gamma effective into Z. So, only one unknown that left out is Amax if you put the value first, because RD can be calculated with the depth using the chart or using the equation which is given here. So, everything is known except Amax. Normally if nothing is given, then Amax can be linked with the seismic zone. Naturally in higher seismic zone, zone 5 it will be the higher. For example, in Amax in zone 5 you can take 0.36, in zone 4 0.24, or then you can have 0.16 or 0.10 like that. So, once CSR can be found in step 4. Now, in step 5, obtain cyclic resistance ratio CRR by correcting standard cyclic resistance ratio CRR 7.5 for which is an earthquake magnitude 7.5, high overburden stress level at high initial shear stress using. So, CRR can be calculated. CRR 7.5 is read from the chart or from the equation which you are going to give later, multiply by MSF. What is MSF? MSF is nothing but it is called magnitude scaling factor. So, MSF is nothing but magnitude scaling factor, short of the and that means depending on the earthquake magnitude the MSF will vary. In IS code 193 suggests that MSF can be calculated using this relation, where MW is the magnitude, moment magnitude of the earthquake. So, this using this relation MSF can be calculated. Normally if you when the magnitude of earthquake is 7.5, then MSF will be 1. So, you will get the MSF equal to 1. MSF equal to 1 for 7.5 magnitude. But if magnitude is higher than 7.5, then MSF is more than 1. But if magnitude is lower than 7.5, then MSF will be less than 1. So, this way we can find the MSF. Now, in this equation CRR 7.5 from the chart or equation, this is known, only 2 factor K alpha and K sigma is left out. And what these 2 factors define, which is here, the correction for high overburden stresses is called K sigma is required when overburden pressure is high, that means depth is more than 15 meter, then only we this require this correction, and this correction can be found using which is equation given sigma V effective overburden pressure divided by atmospheric pressure. And naturally when you use this equation, then both overburden effective overburden pressure as well as atmospheric pressure, they should be represented in the same units multiplied by F minus 1, and where F is a constant which is exponent which is like depends on the soil property. So, F is arranged depending on the relative density of the soil. So, this was K sigma. Then another factor K alpha is coming. K alpha depends on if you have sloping ground. For the gentle ground or for gently slopes or you have the flat ground, K alpha is taken 1. So, both the factors in fact for most of the simple analysis we take both of these factor 1 1. So, if you take 1 1 then they becomes neutralized, they become redundant. So, for most of the analysis these factor may not be considered, they may be required if you have very high overburden pressure or you have the sloping sides rather than gentle slopes. So, now coming to this one, let us assume that we calculated CRR which is CRR 7.5 and this. Then what we do, how to find the value of CRR 7.5. Now, the issue is this here CRR 7.5, how it is calculated. As we said CRR 7.5 can be calculated by using different methods. We are going to discuss in the next few slides based on the SPT, that is standard penetration test data. So, what you do, evaluate the SPT blow count N160 for a hammer efficiency 60% at an effective overburden pressure 1 bar which is 100 kPa, roughly 96 like kPa. So, that is why it is called N160. Why? One subscript says that it is at effective overburden pressure 100 kPa 1 bar, and 60 says it is calculated for a hammer efficiency 60%. So, suppose if your hammer efficiency is different, then this can be calculated. EM is the measured energy and this is free fall energy. So, normally EM will be at least 60% of EFF. So, if suppose if I take very conservative approach and if I put EM equal to point EFF in this equation, then what will happen? If this is the case, then this factor become 1. If it is 80% like EMM is 0.72, it will be 1.2. So, normally this ratio will not be less than 1. So, for the conservative side many times this ratio is taken 1, as a result this equation, this part is neutralized. Now, two other factors are, what is NM? NM is the measured N value of N using SPT data in the field, while Cn is a correction which is called correction due to effect overburden pressure, and this correction can be applied using either this equation 0.77 log 10 2000 sigma V naught. Here sigma V naught is in terms of kilopascal, kilonewton per meter square, or using this equation. In this equation sigma V naught and Pa, they should be represented in the same unit. So, it is not necessary that it should be in kilopascal, but the unit of Pa and sigma V naught should be the same. As a result this ratio will be neutralized, and this says ultimately this Cn which you find should be less than or equal to 1.7. So, the code suggests that the value of Cn in the calculation of this Cn in this formula should not be taken more than 1.7. So, this is how we find the value of N160. Once N160 is known, but it has been observed that this N160 which you are obtaining is for the clean sand, where you have the percentage fines is less than 5%. But it has been observed that the presence of fines affect the SPT resistance, and how they affect the SPT resistance. When the fines increases, then the SPT resistance will increase or liquefaction resistance will increase, and when the liquefaction resistance is increased, that liquefaction resistance increase in liquefaction resistance can be taken care that we increase the corresponding value for the clean sand N160 CS, that is for clean sand here, and if you have this some constant alpha and beta that depends on your fine content. So, in this list when fine content is less than 5%, then alpha equal to 0 and beta equal to 1. So, that means N160 CS will be same as N160. When between 5 to 35%, alpha can be calculated using this equation and beta from this. But if your fine content is more than 35%, then alpha is taken 5 and beta equal to 1.2. So, this value of alpha and beta depending on the fine contents can be taken from this list, and as a result finally we are able to calculate what we call N160 CS, and that is then the value of N160 for clean sand. Now, as we discussed, there are charts was given by Yao et al. If you recall, these are charts which we have already discussed, but to find the value of CRR, and this CRR which you find from this chart is for 7.5 magnitude earthquake. So, basically the CRR which you obtained from this chart which is CRR 7.5. This can also be obtained without using this chart, using some equations which is given here, and these equations are coming from the IS 1893. So, this equation, in this equation on the right hand side you have only one parameter which is N160 CS. That means this is the value of N160 which is for the clean sand. That means correction for the fine contents has been already applied, and once CRR 7.5 is known, then what you do, you can find the value of CRR, which is we already discussed. CRR is find out from this equation. So, CRR is here 7.5 is known, then CRR is obtained, and then finally what we call the factor of safety against liquefaction is found simply ratio of CRR versus cyclic stress ratio. If your factor of safety is less than 1, then soil is assumed to be liquefied, otherwise not to be liquefied. So, this was the case when we using this chart, but in the code IS code these charts are given like this. In the IS 1893 the charts are given for 5%, 15% and 35%, and this is again for 7.5 magnitude earthquake, and you need to apply the correction factors as required. It can be observed the CRR required to initiate liquefaction for when N160 increases, then it will increase. Now, the last part of this lecture, this even on the SPT resistance and the data, it has been observed that the cyclic resistance ratio, it is influenced by the plasticity in the soil, and not only one side is the fines. Here when we talk about fines, it means they are the non plastic fines, non silts and other things, but in case you have plasticity some PI, then they also influence resistance, and it has been observed that they try to exhibit excess pore pressure. As a result, the liquefaction resistance increases, and laboratory tests also indicate that little influence of plasticity indices. If Pi is less than 10, then there is no effect, but if Pi is more than 10, then there is effect. So, what if factor F is, if Pi is greater than 10, then you use factor F equal to 1, but if your Pi is greater than 10, then this equation should be used, where the value of F which you obtain from this equation will be more than 1. So, the CSR which you obtain, this should be actually CRR here, the CRR which you obtain from the charts or the equation should be multiplied by this factor F, and then we use the same for further calculation. Since most sandy soils, the man-made fields have indices, the effect of fine plasticity is usually small, because Pi less than normally less than 15. So, as a result the effect of the plasticity is considered to be small on this. And then you have the data from strong ground motion. The cyclic resistance ratio CRR required to initiate liquefaction decreases with increasing magnitude. So, this was all about. Thank you very much for your kind attention.